Hello everyone, welcome to our webinar today, Touch Current Testing 102. This follows up from our last webinar, Touch Current Testing 101. We'd like to introduce our team here today. I'm your presenter, Bishan Patel. I'm an applications engineer here at Associated Research. Joining us today as a panelist is Ryan Fink. He's the territory sales manager. And we also have Allison Oba. She'll be the organizer for this webinar. Before we get started, a couple of quick notes about the webinar. There is a question and answer utility that you could use. If you have any questions about the material that's being presented here, Ryan will be answering this question during the webinar. Also, if there's any questions that are not answered during the webinar, we will be emailing responses within the email. If you have any questions or concern about the audio or slides that about the presentation, please use the chat box to ask questions to Allison Oba. Also, a quick reminder, this webinar is recorded and will be available online within a few days. If you'd like to get a copy of the presentation, please email Allison Oba. Her email address is allison.oba@arisafety.com. Again, just some quick notes about this webinar today. Before we get started, a recap of what was covered on the previous webinar. We took a look at what the shock hazards are, what potential shock hazards the standards call out for, and what testing that needs to be performed to avoid the shock hazard. We want to mitigate the potential of the unit or the device that you're testing posing a shock hazard to the end user. We also looked at the effects of current on a human body and how a human body will react to different levels of currents. We also looked at how a human body impedance network is measured or determined using network of resistors and capacitors. This is what the current will see as the human body comes in contact with any kind of electrical source. We briefly looked at what leakage currents are. We described leakage current and the various barriers the leakage current will flow through. And we also looked at what touch current is. Now, we defined different types of touch current and briefly looked at how this touch current could be measured. And then the webinar went on to show some demo videos of different types of tests. For today's webinar, we're going to be mainly focusing on medical equipment testing, ME equipment testing, and also the 60601 standard, 60601-1 third edition standard. The reason for that is the medical standard calls out for a more stringent test when it comes to leakage current, and there's different types of leakage current it wants you to test for. The currents could be touch current, patient leakage current, patient auxiliary current, and mains and applied part leakage. We'll go through the definition of all these types of currents and also show you different ways of testing this with a video demonstration. We'll start off describing what the leakage current descriptions are stated in the standards, and also look at how this measurement is made using measuring devices. Again, we'll look at 60601 third edition standard and actually go into the standard, look at the different figures that it mentions, and on how to perform medical equipment touch current testing. Again, just like last webinar, we also have some more additional videos that demonstrate how to perform these various types of leakage currents. So let's get some definition that are stated in the standards for different types of leakage current. First one is touch current. Touch current is listed in the standard as electric current through a human body when it touches one or more accessible part of an installation or of equipment. This definition comes from the IEC 60990 second edition. This is a standard that describes methods of measurement of touch current and protective conductor current. What touch current basically means is when a person comes in contact with the housing of your equipment or any accessible part of your equipment, what is the leakage current that will flow through the person? This is also known as an enclosure leakage. As you could tell, enclosure leakage would be anything that's the housing or any accessible part of your equipment. Next, we'll take a look at patient leakage. The definition for patient leakage is current flowing from the patient connections via the patient to earth. This definition also, there's a secondary definition for current originating from unintended appearance of voltage from external sources on patient and flowing from patient via the patient connection of an F-type applied part to earth. We'll get into the definition of different types of applied part on the next slide. For this, patient leakage is more of to do with when you have medical equipment that actually make conductive contact with the patient. For example, you might have ECG electrodes that connect to a patient, and you will need to run some leakage testing on these electrodes to make sure they're within the standards. Again, patient leads are when you have one or more patient lead connection that actually are forming a conductive path to the patient or are attaching to a patient. A patient auxiliary is a similar test, but this time we're measuring between the two separate types of patient leads. So if your product had more than one patient lead, and you wanted to measure the actual flow between the two patient leads, your current requirements will fall under patient auxiliary. Then we have the mains on applied part test. The mains on applied part test is actually applying mains voltage on your patient leads and seeing if there will be any extra current that will flow through the person that comes in contact with the leads and mains voltage on one end. Again, the definition comes from IEC 60601-1 3rd edition, the medical electrical equipment standard. Before we get started for the rest of the webinar, we do have a quick poll question here on what type of leakage test you currently perform. I have Alice and Oba put up the poll for her.
Hi all, thank you so much for voting. I'm going to close the poll right now. So we asked, what type of leakage tests are you performing? And 90% of people stated that they perform earth leakage tests. 71% of people stated that they perform touch current tests. 29% of people perform patient leakage tests. 19% of people perform patient auxiliary leakage tests. And 33% of people perform mains on applied parts. Thank you all so much for voting.
Thanks everyone for voting. Let's move on to the next slide. We'll be discussing the different types of patient leads connection, and I'll go over the poll results when we get to that next section of this webinar. So when you have your product, you have patient leads that are they're attaching to the patients. The patient leads could be classified in two separate classifications: B-type applied part, or it could be an F-type applied part. For B-type applied part, it provides protection against electrical shock, usually through having a reference to ground connections. And most of the time, the B-type applied part is usually referencing to ground to provide electrical shock. For an F-type applied part, this is actually providing isolation from the rest of the medical equipment or ground, and this F-type applied part are usually isolated and from the rest of the equipment, also ground. Further, this classification goes into two separate patient lead connection. One is type BF and the other one is CF. For type BF connection, this is a patient lead that would have provides a higher degree of protection against electrical shock comparing to a B-type connector. And an example again of type BF part would be ECG electrodes, where it's making connections to a conductive connector to patient, but not necessarily any direct contact with any kind of cardiac applications. For a CF type applied part, you're actually making direct contact to any kind of cardiac applications, like during a surgery when you're using an electrosurgical generator. Anything that comes in direct contact with the heart would be classified or any as a CF product. This is meant to provide the highest isolation from electric shock. So how is this current measured? The current is measured using what we call a measuring device. The measuring device is a network of resistor and capacitor, and it's trying to emulate human body impedance. So this is what the current would see when it comes in contact. When a person comes in contact with an electrical circuit, how is that represented through the view of the circuit, electrical circuit? And that's what a measuring device is. It's basically simulating the human body impedance. Now, the test also calls out for different types of conditions. So there's a normal condition when your product is running normally, and there's also single fault condition. Single fault conditions are where you have your open neutral connection. You could have a reverse polarity on your mains input, or you could have a ground pin that's been disconnected, so an open ground condition. So the standard actually calls out for you to test in a normal condition along with different types of single fault conditions. The main question to ask here is what is the severity of the electrical shock that somebody could potentially receive when either attached to your patient leads or when coming in contact with your medical equipment. Here's a quick look at what our Omnia series offers. This is screenshots from our front panel of our Omnia 2 series instrument. On the top left, you're able to select different types of measuring device. You'll see that medical device is chosen, the IEC 60601. Then on the top right, you have your IT equipment. Again, a standard and the figure from the standard is listed, plus the resistor and the capacitive network is shown. On the bottom, you have the electric spa. The MDs are defined in the standards, and they do vary between different standards. Let's take a quick look at how the connections are made to a tester. Normally, you want to do your touch current test with the unit being powered on. So you want to be able to provide some kind of power to for your device. In our Omnia tester, the power is provided via the line neutral connection, and also the ground is connected to the ground on the back of the instrument. We do use probe high and probe low to run the multiple different types of tests that we could run for the leakage, and I'll show you later on how those probe high and probe low are used in the standards. Quickly take a look at the circuit diagram. Again, this is your normal, the DUT is on your right. It's being plugged into your electrical tester or the line leakage tester. And internally inside the tester, you want to be able to provide both the line and neutral, basically the power to your instrument. You want to also be able to simulate some conditions. So in this case, there's your switches, S1, S2, and S3, and we'll go through how these switches interact. Again, taking a look at how a normal condition is. When you have your normally operating condition, your DUT is plugged in, they're receiving power to line and neutral. At this point, your MD is going between the enclosure of your DUT, which is the outer shell of your DUT, and the reference point, which is the neutral or the lower end of the transformer. In this case, both sides of the MD is shorted, and you will see nominal leakage current. When you have a fault condition, a single fault condition called open neutral, in this case, your unit is, the neutral opened up and the unit should be powering down at that point, but the MD is still shorted between ground pin on one side, ground on one side and ground on the other side. They're still not seeing any more leakage than our normal operating condition. You also have your reverse polarity. This is when S2 will be switching, and this is where line and neutral are reversed. This is simulating a condition where either the line neutrals are switched where the unit is plugged in, or any kind of form of fault that reverses the polarity. And our third condition is open ground. So the S3 is your ground pin. As you could see, when the ground pin is open up, only path for the current to flow through is through the medical device and through the medical device going past the measuring device. That's the MD with a little square around it. Again, we'll see the similar diagrams when we look at the standards, and we'll go over how the standards list out these conditions. Going back to the survey today, the survey results were pretty close to what we normally see, that earth leakage, or as known as the earth leakage, and figure 13 that's referenced. 90% of you perform the earth leakage test. This is measuring the current that would normally flow between the line neutral and the ground pin. 71% of you performed the enclosure leakage, which is also known as a touch current. This is, again, somebody coming in contact with the medical equipment and then measuring the current flow through the person to ground. We'll also be referencing some of the other testing that could be done, which is the mains and applied part, and also the auxiliary. Auxiliary patient leakage comes from the standard 60601 figure 19, and the patient, the actual applied part leakage comes from figure 16 in the standard. This document here is available on our website. It's what we call our standards guide. The standard guide allows you to look at what section of the standards that the requirements are, what section of the standards that our instrument could perform the testing to, and also gives you some idea of what are the criteria for either the pass criteria, and also what is required. Let's take a look at some of the conditions here real quick. The requirement listed in section 8.7 is listed as leakage current and patient auxiliary current. It calls out for testing in both normal condition, like we saw earlier, and single fault condition. It also calls out for testing at supply voltage at 110% of the mains rated voltage. What this means, if your product is rated for 240 volts or 115 and 240, you want to be testing at 110% of the 240 volts, which will be 264. This is a higher of the two voltages. Same thing applies for the frequency. If you have a product that's rated for both 50 and 60 hertz, you want to be testing at the higher frequency. Let's take a look at the pass criteria. If you are performing the earth leakage, you would know that the current needs to be less than 5 milliamps for normal condition, which is your product operating normally, or 10 milliamps for any single fault condition. This could be open neutral, open ground, or reverse polarity. When it comes to touch current, we have the normal condition. The touch current is a lot less now. It's up to 100 microamps. Again, this is normal condition, and 500 microamps for single fault condition. And what we're going to look at next is the patient leakage current. When you're performing your patient auxiliary test and also your patient leakage, what kind of numbers you should be looking at and where to look at in the standards. We refer to this as table 3 and 4 in our standards. So we're going to quickly take a look at table 3 and 4 of the standard. I have the 60601 standard pulled up here. I'm looking at IEC 60601-1 3rd edition, and what we're currently looking at is the requirements for patient leakage and patient auxiliary currents. So the standard calls out for, depending on the type of part you have, if you have a type B applied part, again, type B applied part is your applied part that does not have conductive contact. I forgot to mention earlier that an example of a type B applied part would be something like a hospital bed that usually comes in contact with the patient but does not necessarily conduct any conductive contact. When we move over to our applied part, BF applied part, and then you have your type CF applied part. Taking a look at the patient leakage current. This is the current that flows from the patient connection to earth, and you can see the values listed here and the measuring circuit to use. This references figure 15 for patient leakage and also figure 19 for patient auxiliary. Again, we'll be looking at these two figures later in this webinar. What I did want to cover here real quick is the AC versus DC. Our instrument offer filtering devices that could filter between AC and DC current. And if you had older devices that cannot do the filtering, most likely the AC limits apply in this case, because the AC requirements is a composite of both AC and DC. In this case, they're just separating out, and our instrument is able to separate out both AC and DC separately. So if you're performing tests and if you want to check for your DC current limits, you would come into this table, take a look at what type of part you have, and either for a single fault condition, which is 50 microamps, and then you have your a normal condition, which will be 10 microamps. Again, the most stringent requirements would be for the CF part that comes in direct contact with any kind of cardiac application. Again, you can see in the table that the current requirement or the criteria is almost a tenth of the requirement for a B-type applied part or even a BF type. So the CF applied parts are a lot stringent, and the requirements are for the current are a lot less, because the products or the applied part could actually come in direct contact with the heart. So that was table 3 of the standards, and I'm going to quickly take a look at table 4 here. Table 4 mentions any kind of external voltage. Imagine if your product had a signal input or signal output, usually called SIP-SOP, which is if there was any external voltage on that port, what kind of current limits are allowed. So as you can see here, this is 5,000 microamps for voltage on the external connections. There's also other voltages that could be part of your device. If you have any point on your product that's not protectively earthed. And when we're taking a look at figure later on in the webinar, I'll show you where it mentions doing different types of testing. So let's talk about touch current. So when earlier we described touch current as being a person that could come in contact with your enclosure or the body of your instrument, and the resulting current that goes to the person to ground. This is described in figure 14 of the standards, and we're going to quickly take a look at what figure 14 describes. So let me get to that page here in the standards. I'm going to get back to the top section in a minute here. So this is figure 14 in the standards called measuring circuit for touch current. If you take a look here, what the circuit is representing is what we saw earlier, where your mains input is supplying the power for your instrument to turn on. There's a voltmeter that goes across line and neutral. You have your switch S1, which opens up the neutral connection for a single fault condition. You have your switch S5 here that simulates reverse polarity, and then you have your S7 switch, which is protective earth conductor, and this is to simulate the open ground condition. A thing to notice here is where the MD falls into. So this is where a measuring device, again, measuring device is just a human body impedance network. So this is simulating a human body coming into contact with your DUT, which is on the right here, and then measuring that current going back to the neutral or the low end of the transformer side. So this is how the touch current is mentioned in the standard. Again, depending on the instrument you have, if you have any non-protectively earthed contact points on your instrument or medical equipment, you might need to perform a secondary test that goes between two of those points, and which is the MD listed on the right here. A short notice, a point about the T2 transformer here. This is where we had our when we mentioned the mains on the signal input output. So P1 connection here is your SIP-SOP connection, and you want to apply mains voltage to that point and measure the resulting leakage current through this MD when there's a line voltage coming into at this point. There's also a reversal of polarity here, so this is also reverse polarity, and this voltage for this also needs to be at 110% of the operating voltage of your product. Again, this is a separate transformer, isolated T2 transformer that will apply line voltage to your SIP-SOP connection and measure the resulting leakage current through the MD measuring device back to the system reference. So saying that, let's take a look at how a touch current test is performed, and we'll be taking a look at a video, and I'll be describing what the video is showing as.
Guys, I have several of them.
All right, so real quick, before we get started, I wanted to show you how this is performed using a line leakage tester. In this case, it's an Omnia tester. On the back of the Omnia, we have connections for line neutral, ground, probe high, and probe low. Again, line neutral will provide the power to the DUT to power on for this test. Ground is the ground connection, and then we have probe high and probe low condition probes to actually measure different types of leakage. And this is what a universal adapter looks like for plugging in different types of DUT, and alligator clips on the end of probe high and probe low for making good contact with the product. Next, we're going to show you how to set up the actual test in our tester. Again, the requirements for the test usually comes from the standards and the tables that we referenced earlier. And what we're going to do here is quickly turn on the internal power source. Our Omnia does come with the internal power source, a 500 VA power source. And the first part of the video is actually just turning on the internal power source. You do want to turn on the power source and supply at least 110% of your normal operating voltage. And let's skip through this a little bit. And okay, so we'll get to how to set up a line leakage test. In this case, we're going to set up a test with leakage high of 1,000 microamps, and then we have your volt high and volt low limits. The standards also calls out for making sure your voltage, your unit is operating at normal voltage, and this is where your voltage detector comes in. So we have a volt high, volt low settings. We want to make our our instrument or your medical equipment does not go below a certain value or go above a certain value when you're performing line leakage. For this, we're going to give dwell time, which is the actual testing time of 5 seconds, and a delay time. Our tester has a delay time that you could input. This allows your instrument to power on properly and get into a good ready state for the leakage current measurements. Okay. If you notice on the right side, we have our conditions or our switches. We have our neutral, which is closed for this test, reverse, which is off, and ground, which is closed. In this case, we're doing a normal condition. In a normal condition, you have your neutral closed, your reverse off, and your ground closed. We will be selecting a measuring device for this. It will be the 60601 standard. Again, this is where we actually select which measuring device to use for this particular test. Depending on what test what standard you're trying to comply with, this is where you come and select the actual measuring device. For touch current, this is where your probe high connection comes into play. When you're doing touch current compared to ground connection or protective earth conductor current, doing touch current, you have an actual point of testing, which is where the probe high will connect to. Again, this diagram references back to the standard. You have your probe high and your probe low connection. For touch current, you want to be able to turn this probing condition to probe high to line. At this point, you will be measuring the current that will flow between the probe high here, going through the MD back to the reference point on the neutral side. Again, this is how you would set up the probe condition for doing touch current. And we want to also make sure we have the proper voltage set for this product. So we're going to go into our instrument and set it to 120 volts. And this is where you would set the actual voltage, the test voltage for your product. The second test we're going to add here is going to be an open condition. So we're going to do a single fault condition. We're going to open up the ground and see what kind of resulting leakage current we might get. Again, open ground should result in the higher number of leakage current compared to the other test. In the next video is, let me just wait, give me 1 second. So we have our tester on the left, the Omnia tester that has the 2 files loaded. We also have a product on the right. Currently it's a laptop that's being used. Since this is a class 2 product and does not have any accessible parts that are conductive path, usually it's plastic. So the standard calls out for simulating a palm of a human body, and we're using aluminum foil to act as a human contact point, and this is where it's covered over. This is measuring the actual leakage that might be coming through the keyboard or any of the any sides of the either the screen or any part of the DUT itself. But we're measuring the leakage current between the product and the aluminum foil. What I did want to show you here is how this connection is made. So we're using the probe high connection. Probe high is connected to the aluminum foil, and this is what becomes one side of our measuring device, which is the probe high, and the second side of the measuring device is connected internally to the line reference. Again, the next video will actually show you the test being performed. So when we're performing this test, you could see the voltage that's being applied is 120 volts, and the resulting leakage current, which is for normal conditions, you could tell the leakage is around 0.4 microamps. And now we have the single fault condition here, noted by the red ground pin, which indicates the open ground condition. Also, taking a look at probe condition is probe high to line. The resulting leakage is also 0.4. In this case, it is what is expected out of the laptop, because the laptop is a class 2 product that does not have any conductive areas or on the surface of the product. There's no accessible accessible metal parts, and that's why you would expect a lot less leakage current. Next, we're going to take a look at patient leakage. In the patient leakage, we're going to be taking a look at figure 15 of the standard. Again, we looked at taking a look at figure 15. Let me pull that up real quick. So this is the figure 15 labeled measuring circuit for patient leakage current from patient connection to earth. So if your product had patient connection, referenced here by connection point 4, these are your patient connection that you attach to patients, or patient leads again. On the left side, you have again your mains voltage. You're providing voltage via isolation transformer, and you're measuring the voltage with the voltmeter across line and neutral. You still have your conditions S1, switch S1, S5, and S7, which will simulate your normal condition and also single fault conditions. And the main thing to look here will be where the placement of your measuring device is. As you could see, the measuring device is connected directly to your patient leads, and it's measuring the current that will flow through the patient lead back to the system reference. Again, this is for attaching patient lead to your MD and measuring the current resulting leakage current. So let's take a look at how this is done using any leakage tester and how this can be performed. Sorry about that. We're going to go in here and set our parameters according to the table. Again, for patient leakage, you have a lot lower current criteria. So in this case, we want to lower, the requirement would be 500 microamps. So we're going to set our leakage high here to 500 microamps. We're going to set our conditions here. The main point to look for here would be where your where your probe high connection falls in. So again, your probe high is still connected to your patient leads, and we're going to be attaching those patient lead to probe high. Again, we're just setting up the test here, setting the proper leakage requirements, and we're setting the proper switch condition, which is open ground in this case, which will give us our biggest leakage current if there was any. And then we're going to do one more condition. This will be open neutral. Again, there's 8 different combinations of fault condition that could occur, single fault condition, when you have 3 different switches. That was just setting up the test. We're going to be using one of our HiPod tester as a medical device to perform the patient leakage. What we're doing here is we have our tester here that has one connection point, which is connected, acting as a patient lead, and we're connecting that point to our probe high connection, and this will put the measuring device between this point here and the line or the reference back to the lower end of the transformer. Again, this connection was for patient leakage, so we're actually testing the lead that's coming out of our tester back to the system reference and putting the MD between that point. Again, we're going to be running this test. The unit is powering on. The resulting leakage current when the ground is closed. You can see with the condition here at the top right is a normal condition where none of the faults are occurring, and your probe conditioning is probe high to line. Again, this is a normal test, which is called the normal condition, and everything is working properly. And the resulting leakage current is 0.2 microamps. The next test here, you'll see the red icon next to the ground. This is simulating an open ground condition, and you can see that with the open ground, there was a little bit more leakage that goes through the measuring device. For the last one with open neutral connection, you could see that the open neutral connection actually causes the unit to power down, and in this case, you're back to 0.2 microamps. And again, in this case, in open neutral, your unit normally does not power on, and you will see minimal leakage current at that point. So that was your patient leakage testing and how you perform that when you have a patient leads that actually connect to patients. Next, we're going to take a look at patient auxiliary. This is figure 19 in the standards. Again, figure 19 in the standards, we could take a look real quick. Let me pull that up. All right, so this is figure 19, labeled measuring circuit for patient auxiliary. If you have more than one patient connections, you want to perform what's called a patient auxiliary. This is actually measuring the leakage current that flows between the 2 patient leads. If you have similar types of patient, if you have leads their function is similar, you could tie them together. And you want to measure it with the leads that don't have the functionality, same as the previous the leads. Basically, the product itself would dictate which type of test you will run. So if you have a product that had all the patient leads were doing the same function, you could actually tie them together to run the MD test, or you could actually have separate functionality on your product, and then you want to test between the patient leads. Again, same connection. We have our source, which is a T1 transformer, providing power to our instrument, which is here labeled 1. Your connection points, again, they go between the patient lead. Measuring device is what we're going to place between points 4 here, and those are the patient lead connection. Again, since the MD is between 2 separate locations, this is where we're going to use our probe high and probe low connections. We want to place probe high at one patient lead. We want to place probe low at the other patient lead. So this will put our measuring device, our human body, between these 2 points. And we're going to be measuring the resulting leakage current when this unit is functioning normally. Okay, so let's take a look at that test. Have a video here for that. This is performing patient auxiliary test.
It's a little bit of a different situation.
Okay, and again, we're going to be using the same setup we used earlier for the patient connection, and this time we're going to change the probing condition. Again, the reason we're changing the probe condition is we want to place the measuring device between two particular points. This is where our probe high and probe low that I mentioned earlier comes into effect, and we want to place these connections between the two patient leads. So we're going to go through setting up and making sure all three tests have the correct probe conditions. Again, these are the same. This is the same test from earlier, and we're just changing the probing condition to now reflect what's called a patient auxiliary test. The way we have set up our DUT, again, we're going to be using the same DUT that we used earlier, but at this time we're going to be using two separate points or two separate connection points in our DUT. We have, again, you have your probe high and probe low connected to these 2 points, and we're going to be measuring the leakage current that will flow between these 2 points. This instrument has other points, so of course you would want to run separately for the different, however many leads you have, you want to run separate tests for each leads you have. All right, so we're still getting power for this DUT from our Omnia source, and it's still connected to the back. And we'll quickly take a look at how the test is ran and what kind of resulting leakage current you see. As you can see here, even during normal conditions, there's plenty of leakage current between those 2 points, around 280 to 90 microamps. And then again, with the open ground, you're seeing a little bit more leakage, 294. So that leakage is actually between those 2 points on front of our tester. And then we have our open neutral condition. Again, open neutral condition, the unit is powered down, and there's no more current flowing through the measuring device. Okay, so this was an example of how a patient auxiliary test is ran according to the figure 19 in the standard 60601. I did see that we have 33% of people doing mains and applied part testing. This is a specialized testing due to the nature of having applying line voltage on your the patient leads. We do have a quick video here to show you. This will actually show you the process of doing the mains and applied part testing. But before we get to that, let's quickly take a look at figure 16 on how this test is performed. So in standard, there's a standard, and we'll take a look at figure 16 in the standard. Okay, again, this is going to be demonstrated by our video, but I want to quickly go over mains and applied part here. Top half of the circuit you already seen earlier. Well, this is the French version, so get to the English. So we have our T1 transformer applying voltage to our instrument or DUT device under test, and your measuring device is still between the patient lead, but now you're going to be applying voltage, a line voltage coming from a secondary transformer T2 with that goes through a current limiting resistor, which is an optional resistor to protect the operator. And there's also a reverse polarity condition. So this is applying voltage on one end of your measuring device. I'm sorry, applying line voltage on one end of your measuring device, which is connected to your device through the patient lead. This mains and applied part could be looked at as an example where when you have a patient that could come in contact with a line or source, a line voltage, a secondary source, which will be any kind of other line voltage, and they're still connected to your DUT. So what effect would the person have, or the person have, if they experience this situation where they're connected to line voltage on one end, connected to your instrument or your patient lead on the other side? Again, this is represented here by attaching one side of the measuring device to line voltage via a current limiting resistor, and the other side is connected to your device or to the medical equipment through your patient leads, listed as 4 here. So there's a video. It's a long video here, about 10 minutes I want to say, and I want to play this video. But I would also recommend increasing your volume on your PC or something. I think the volume's a little low on this video, so so you guys could hear better, I would increase the volume on your side.
Welcome to the Associated Research line leakage testing demonstration. The purpose of this demonstration is to show how you can automate line leakage testing per the medical device standard for running earth leakage, patient leakage, enclosure leakage, patient auxiliary leakage, and mains unapplied part testing. Today I've provided a simple example showing how this can be done. What I'll be using today is the AutoWare 2 software, which we use to communicate with the instruments, as well as an Omnia 8207 unit, which is a 7-in-1, does AC high pot, DC high pot, insulation resistance, ground bond, ground continuity, functional run, line leakage testing, and also has a built-in 500 VA power source, which we will use to power up the medical device for this demonstration today. Also along with this, I have two multiplexing ST6540 scanners. Here I have a 16-channel master, and here I have an 8-channel slave. Before we get into setting this up through the software and showing you what the parameters are for each step, I'm just going to briefly show the connections that I have here for this particular demonstration. So there's a lot of wires going on back here, and hopefully you can see this without too much difficulty. Basically what we have here is a medical device with 4 patient leads. And I have the 4 patient leads connected here. You can see I have 3 patient leads connected here and the 4th here. Those are going back to the master channels 1 through 4, patient lead 1, 2, 3, and 4. I also have a protective earthing connection from the medical device, which is going here into channel 8 on this master scanner, as well as channel 3 on this slave scanner. And I'll explain in a moment why I'm using 2 scanners and why I have 2 PE points. But I basically just wanted to show how the patient leads are connected so that we can run this in an automated sequence. Additionally, what I have is I am using a linear 1 kVA power source to simulate my T2 or my transformer 2 for my mains unapplied part testing. So what I have here is 132 volts going through these lines, and you'll have to forgive me, I don't have professional fixturing here, but what I have is line and neutral from the source going through a series of resistors up to the various scanner channels. Now you'll notice I have 2 sets of wires coming out from the source. I've paralleled them, and I'll show you why. This also explains why we have an extra PE connection. I have line and neutral going to these 2 scanner channels, which are 6 and 7 on the master scanner, and then PE goes to channel 8. And then I additionally also have line and neutral going to this second scanner, as well as PE going to channels 1, 2, and 3. The reason is because if you look at the standard and the way these tests are run, you actually reverse polarity at some point from T2. So here we can see T2, and we have line, neutral, going through a resistor, through the measuring device, and back up to the patient lead. Well, at the same time as running line through this resistor, I need to tie neutral in to my protective or reference point. So by putting them through 2 separate scanners, I have the capability of tying these points together without including it in the measuring circuit. So that's why I've used 2 scanners in this instance, essentially to provide isolation. So what I'm going to do here is put the camera in the mount and run through a sequence of tests for this demo. So what you're seeing here is actually the AutoWare 2 program, and this is how I set up the tests. A little easier than doing it manually. So I've already created a line leakage sequence, as you can see here, with multiple steps. Now, I'm going to double click on this to show you the various parameters that we're looking at. Now, this is showing me all the parameters I have set up for this test. Now keep in mind this is a demo, so I've kept the limits here pretty much the same across the board for all these tests. I have a 6,000 microamp high limit, 0 microamp low limit. I've set my voltage high limit to 135 because, as you can see, for this particular medical device, I'm running 110% mains, which is 132 volts. And I set the internal power source on the device to 132. so that it can run the product at that voltage. I set my voltage load limit to 129 just to make sure that my source is working properly. If it happens to dip below that, I'll get an error message. I've set my delay and my dwell time both to 1 second. We'll keep it short. And I have my probe configuration set ground to line, which means this is an earth leakage test. I have the 60601 measuring device, and I'm measuring RMS, and I'm measuring a composite signal, AC plus DC, although you do have the capability to use filtering to measure AC or DC only on this particular device. We also here have our fault conditions, our neutral, our ground, and our reverse fault condition, and our continuous run, which basically will keep the product powered up, of course, given that you don't have an open neutral condition, in between steps. Given that this is an earth leakage test, we currently don't have any of the scanner channels set. So that's actually what I've done for these first 8 steps, because if we consider all 3 fault conditions for earth leakage, that takes us out to 8 steps. So on the 9th step is where I actually start doing my patient measurements. Now, I didn't do 8 steps individually for each patient measurement, but when you see how I'm doing this, you'll get the idea behind what I'm doing. You can certainly extrapolate and do as many tests as you want in as many patient leads. Now recall, on my master scanner, which is what I have set here, my SC6540 address 1, I had patient lead 1 connected to channel 1. So I'm setting, with red here, patient lead 1 high. Green is low. So I'm setting patient lead 1 high, and I'm also setting channel 15 high. And if you recall, I set my probe high to channel 15 and my probe low to channel 16. Those probes are simply coming from the Omnia, and they're just probing points that the Omnia uses to reach out and go across various points so that the MD can get a solid measurement. So once again, I set probe high to channel 15 and probe low to channel 16. Since I'm just doing a patient leakage test here, I'm only selecting my probe high to line configuration because I'm measuring patient leakage back to the line or neutral reference of the system, depending upon the polarity switching while you're running these tests. As you can see, I'm still running 132 volts, and I still have continuous on. And basically all I have here is I have my probe high, which is again connected to channel 15, going out to short to patient lead 1. So I basically simply repeated this process for patient lead 2. As you can see here, now I have patient lead 2 high connected to probe high, which is on my channel 15. For the next step, I have patient lead 3 high connected to probe high. And then finally, of course, I have patient lead 4 high to connect to my probe high. So that pretty much takes care of showing what the patient leakage is all about. And we have a few more steps here. 13, 14, and 15 outline patient auxiliary testing. So now what we have are very similar parameters as you saw in the previous steps. However, you'll notice I've changed my probe configuration from probe high to line to probe high to probe low. So now I'm using 2 probing points, much like you'd use with a multimeter if you were just taking 2 probes and going across 2 points with the 60601 measuring device. And I have patient lead 1 high set to probe high and patient lead 2 low set to probe low. So essentially, we're just measuring from patient lead 1 to patient lead 2 while the product is running at 132 volts. And I repeat this process for the remaining steps. Now I'm going from patient lead 1 to patient lead 3, still keeping probe high and probe low in the circuit. For step 15, I simply am taking patient lead 1 to patient lead 4, probe high to probe low. Now for steps 16 and 17, this is where I illustrate the mains on applied part tests. Recall that I brought line neutral and protective earthing so that I can complete the circuit at the same time providing isolation. So I'm still on a probe high to probe low configuration, only this time I've got channel 6, which is line voltage. This channel here is line voltage coming from the isolation transformer T2 connected to probe high through that resistor. And then I've connected probe low, channel 16, to patient lead 1, which is on channel 1. So that takes care of the measurement circuit for probe high to probe low through the MD on the mains on applied part. However, I still need to complete the other side of the circuit. So on the slave, I've tried channel 2, which is neutral, to the protective earthing point, or our reference point, shorted together to complete the circuit on that side, but at the same time, now it's not involved with our measurement. And I've simply now repeated this process for the next step, but now I've reversed the polarity of the lines coming from transformer 2. So now I have channel 7 high, which is the neutral of the circuit, in contact with high, and channel 16, which is probe low, in contact with patient lead 1. And then we'll see on my other scanner, now I'm bringing line voltage from transformer 2 in contact with the PE point and tying those together as it would be exactly on the diagram for figure 17 for a mains on applied part test. You can well imagine you can extrapolate this out to as many steps or patient leads as you see fit, given that you have enough scanner channels to run this test. So I'm going to go ahead and save this information and jump over to my control panel. Now here you can see that the Omnia and the program are working together to load all the files onto the unit. Once it's complete, I'll be ready to test. So I'm going to go ahead and push the test button and we'll watch it run through the sequence. So what we can see here is the Omnia running through the test. We can see the voltage, we can see the leakage current measurement, we can even see the fault conditions here. Currently we're on step 4. Here's step 5, so we're still on earth leakage, and we can still see we have a G to L probe configuration here. Step 7, step 8, and now step 9, we're going to start going through various patient leads. So here we can see probe high to patient lead 1, probe high to patient lead 2, and remember probe high is channel 15, so that's just connected to patient lead 2 here. Probe high to patient lead 3, as this LED goes on, still connected to my probe high to patient lead 4. Then we go into our patient auxiliary tests after this one. So now we can see patient lead 1 to patient lead 2, probe high to probe low. So we have our probe high, probe low here. Now we have patient lead 1 to patient lead 3. And finally, patient lead 1 to patient lead 4. Finally, we have our mains on applied part tests. And here we can see, getting a little more leakage, only about 1 microamp in this case. But now we have probe high to probe low, line voltage connected to probe high, which is channel 6, and probe low connected to patient lead 1. At the same time, on the other scanner, I've shorted my neutral to my protective earthing point because I've tied those points in there. And then finally, on our last mains on applied part test, I flipped the polarity of this circuit. Now we have neutral connected to probe high, probe low connected to patient lead 1, while line voltage and PE are shorted together on the medical device. You can actually see it powered up here doing its thing. And the test sequence has completed. Now, of course, were this an actual run of tests that I was going through, we'd have many, many more steps. We'd have 8 steps for each one of these conditions. But I wanted to illustrate here how with multiple patient leads, you can actually run through and do all of these types of tests without the need for switching out the configuration. Obviously, the main time investment here is working up your fixturing to connect up to the product. So hopefully this illustrates how you can do this in an automated fashion.
All right, we're short on time a little bit, so I want to go on to the next section. And just want to remind there's additional testing that are being covered today, which would be the figure 18, external voltage on metal accessible part, which is not protectively earthed. Basically saying that if you have any point on your the device that is not protectively earthed, you would use figure 18 to perform the test, and also figure 17 for external voltage on SIPs up or signal input output. Before we go, there's some documents that are available for limited time. These are what's called audit survival guide and also installation and operational qualification. I know we'll be posting that link into the chat box for anybody that needs access to it. I want to quickly run through what those documentation is. So once you go to our website and download when you type in everything here, download your the documents, I want to walk you through the process of how to use this documentation. In here we have the audit guide, and we also have a Omnia 2 qualification along with the other qualification, installation and qualification guides. Once you download this, once you download the folder, there's multiple documents in the folder, and I'm going to quickly cover that. I know we're running short on time, but what you want to do is quickly look at the parent document. The parent document actually tells you how the rest of the documents are used. I know many of the companies do have internal documentation that when they're installing new instruments or when they're qualifying instrumentation, you want to make sure the product is performing the way it should, right? So this is something that if you don't have an IQOQ document, you could get started with one, or implement some of our already worked out processes into your own company's IQOQ documentation. Again, we'll quickly take a look at the document itself. So you'll see the scope is mentioned here. Also, the actual documentation that is included in this folder is listed here for the Omnia, depending on the system configuration, which documents to use. You saw the scanner that was part of the video. If you had a scanner, which document to use for that. And then we have a flow chart, an actual flow chart that shows you how this document is to be used. You start off with determining which system you have currently. You have an Omnia with a scanner, you have an Omnia by itself, or you could have one without the line leakage testing, and you could be using software. So we will have all these documentation available in this folder for you to follow this for this flow chart. There's also a page here for additional information for system requirements, basically get you started with the IQOQ documentation. We do look for feedback on our documentation here, and also if you have any comments or anything that you could provide valuable information, we're always here. We could always make improvements to our documentation. And if you have any questions on how to use this documentation, do email us, and we'll definitely get back to you on the whole process of going through IQOQ documentation. All right, that concludes our webinar for today. I know we went over it a little bit. Here's some contact information real quick. If you want a copy of this presentation, you could email Allison Oba. The webinar is recorded, will be available on our website within a few days. Thank you for everybody. Thank you for attending.